solution, the video solution for exam 1 in dynamics. We have a U-Heart outfielder here who's throwing a ball from the outfield with initial speed, leaving their hand at VO at an angle of theta, leaving the hand at height h. We want to, after the ball has left his hand for a duration of t, we want to determine the r dot and theta dot using 0, O, I guess, as the polar coordinates reference. And you must use a coordinate transformation as part of the solution to this. So let me turn my camera on, document camera, let's see if it'll work. Okay, let's see. Are you going to work? There you go. Alright. So for mine, I'm going to go ahead and use the given information. I'm going to have my given as be 100 feet per second and a theta of 30 degrees. And I'm going to start with a height of 6 feet. And what else did I use? I think I decided for a delta t. Let me see. Let me bring this up here. What did I say? What did I use as my baseline one here? I used 2 seconds. Okay. Alright, so I have a time of 2 seconds. So it's going up like that right there. Well, I'm sorry, right there. Right. So this is h right here, and here is like where O is going to be. So it's VO, and this is the theta right there being thrown up. So the first thing I want to do is I just want to check. I have written out a solution thing here. Right. I want to find my VOX. This is going to be 100 times the cosine of 30, and VOY is equal to 100 times the sine of 30. So let's get some calculator out here. I don't know if I'm just going to make this longer video, but I'll try to do it in real time. 30 cosine times right there, so we're going to get 86.60 feet per second, and 100, this should be 50, right? But we'll do it anyway. Sine times, there should be 50. So this is original velocity going up in there. So we want to find out its position after this amount of time. So in the x direction, that's just going to be, we're going to start out with 0 right there, plus VOX times time, or 86.60 times our 2 seconds. It comes out to 173.2 feet. And then the y is going to be y0 plus VOYT minus 1/2 GT squared. I'll write it down below. So that's going to be 6, because it starts out at 6 feet, plus 50 times 2 seconds minus 1/2, 32.2, and 2 seconds squared. So let's see how high up this thing has gone. So we'll start out with, I'll do 50 times 2, and I'll add 6 to it. Right, so it goes 106, and looking over there, and 32.2 times 4 divided by 2, and I subtract it out, and I get 41.60 feet. And as I'm going along here, I'm just going to check my my values that I got the same thing I said before. Yeah, 41.6 feet. Do I need the velocity? Yes, I do need the velocity, because you need to do the coordinate transformation. Now the velocity in the x direction is going to be this constantly, but the velocity in the y direction is going to be the original velocity in the y direction minus g times time, right? So we started out with 50, and I think, wait a minute, I gotta double check. Yes, that's going to be true. 50 minus 32.2 times our time, and we're going to get a negative number. That's because it's coming back down towards the ground, right? So it's gone past the crest of the thing. So 50 32.2 times 2 and subtract, and we get a negative 14.40 feet per second. Okay, so if we want to write out what the velocity is for this thing in Cartesian coordinates, we would say it's 86.60 I plus negative 14.40 J is feet per second. Now we have to, now that's like with the position, but now we want to try to find out where he was, right? So look at like here, so you can see that here's where that would have gone to the path, but it's going to be somewhere like right there, right? So it's aiming downwards along that path. But we want to find, using polar coordinates, where that's going to be right there. So we can draw a line that's going to be R right there, and I think I decided to give this, somewhere I gave it like a new name, like theta something, because this is already theta up here. I might say theta 1 if I decide that's going to be position 1, if I call this position 0. Alright, and so we want to do the coordinate transformations. Well, we first need to find, well, we will need that R in a minute, but we really need that theta 1 right here. So we have the position X and Y right there. So we can get that R is just going to be, move my keyboard here because stop that, square root of x squared plus y squared, or the square root of 173.2 squared plus 41.60 squared, 173.2 squared, 41.6 squared, and we got to take the square root, and I get it's like 178.1 feet is the distance from the ground right by his feet, and that angle, which I decided to call theta 1, is going to be the inverse tan of the rise over run. So that's 41.6 and 173.2, and divide, and we get the inverse tan of that, and we get this to be 13.51 degrees. Alright, so now we have this velocity and we have this angle, so we want to do a coordinate transformation, right? So here's our I and our J, and here's going to be our ER, and then the E theta is going to be this way right here, and here is the angle 1, right? So we got to be careful I can do that here. So our coordinate transformation should look something like this right here. These are I, here's our J, here's our ER and E theta, and we can see that's going to be a cosine for ER and a sine, both positive, and by makes it theta 1. And this one's going to be negative because it's going in that direction, so it's a negative sine theta 1, and then there's a cosine of theta 1. So now we take this and we put it through that. So we say the velocity is going to be 86 right here, times the cosine of 13.51. Right, I'm going to do the i's together at the same time, and then I'll do my plus negative 14.40 times negative sine of 13.51. I think I had nothing there. That's going to be I, and then I'll do the J down here. I'm going to have the 86.60 times the negative sine. Sorry. Okay, careful. We're going to go, did I do that wrong? I'm sorry, I did it wrong. My bad. I was thinking. I wasn't thinking, I should say. I'm talking, not thinking. We got to go the 86I right here. Then we have to take this J and go right there. So it's going to be a positive sign, right? Positive 13.51, right? Did I do that correctly? Yeah, because I want ER. Now I'm going to take and find for the E theta. down here, I'll take my 86.60 multiplied by the negative sign of 13.51. That makes sense, right? And then plus my negative 14.41, and take it times the cosine of 13.51. And that's going to be E theta. So I work out all of these. This is probably the longest part of the problem, is doing that coordinate transformation. E6.6, 13.51 cosine times, okay, we're good there. Then I get a 14.4 and 13.51 sine times, right? And that's a negative right there, so I'm going to subtract that out. So I get 8.0, no, I got 80.84 ER, and that's a positive value. And then for this one, it's going to be a negative value, right? Because you have a negative there and you have a negative there. 86.6, 13.51 sine, and multiply them. I'll make sure it's negative. And then 14.41, 13.51 cosine times, and subtract it, and we'll get a negative 34.24. Let me see if I matched up. My numbers are slightly off for some reason. No. I was looking at acceleration. Yeah, no, I got the correct one. Okay, good. E theta. So that's going to be still feet per second. And now we could do a first answer, because we were looking to find our dot. We know that it's going to be 80.84 feet per second. And then we want theta, right? So this is V, this one right here is V theta. And we know that V theta, right, I don't know if I want to use this clipboard anymore because it gets messed up with the keyboard. That's just right in the keyboard out of the way. There you go. And that's going to be equal to R theta dot. So we want to get theta dot. So we divide V theta by R. So we take a negative 34.24 and divide it by the R that we got all the way up here, 178. 178.1. So we get a negative 78.1 divided. We get a negative 0.1923 radians per second. And that kind of makes sense that it's negative because it's going clockwise, right? Whereas our coordinates, counterclockwise is positive. So the ball is like coming down this way, but it is extending outwards. It is increasing in things. So let's see how much time did that take. It should have been 15 minutes, I think. Yeah, I got 13 minutes this time, right? I timed this out to be a 15-minute problem. I think I actually reduced something to try to get it down below 15. But that was by far the longest problem. We'll take a look at the second problem here then. Let's see, put this up there. And now we have this car, or a group of students are traveling in that car B, and they go into an air show, and they spot the air show, this airplane going at a constant speed around a loop. They start to change speeds, and when they get to this spot right here, we want to find what the relative acceleration is of the car with respect to the airplane. Okay, so the thought process that we're going to go through for this is to figure out what the car's deceleration is between the two spots, right? That goes from here to right there, right, along this straight line. And we have this airplane that starts out up here, but he's going to be coming around, right? So he's got a VA, and here's VB1, and here's VB2, right? And so we're using kind of like where this could be like the driveway or something to the air show, and this thing is going around some central point, like right there. And so this distance is x2, and this distance is x1. So the first thing we want to do, let's find out what the deceleration is going to be between these two spots. We were given the velocity here and velocity there, so we could say VB2 squared is going to be VB1 squared plus 2 acceleration of v times this delta x. All right, so the values that I used, let's see, I'll write these out. Let me see. What values did I use initially for my original problem? I said this was 30 meters or feet, meters, yeah, per second, and VB2, I think he drops down to 20, right? So that's going to be the second one, and looks like my office hours are starting soon. Then we have the velocity of A. I think I have mine is 40 meters per second, and X1 was like 1,000 feet. Let me take a look here. I have it over there too. And so here we go, 1,000. We got 1,000 feet, meters. Sorry. And X2 is, I think I just had 500. And anything else? I guess I gave a Y of 300. I don't think this is actually necessary. I don't think you ever need to use the Y. If we were going to do a coordinate transformation, I think we would need to, for like a polar thing, we would need to do that. But this is more like a path coordinates problem, because I want you to get the acceleration of this. Okay, anyway, so this is going to be 20 squared is equal to 30 squared plus 2 times acceleration of v times my delta x, which is just going to be 1,000 minus 500. Right? So I get acceleration of v if I do that. So you have 20 squared and 30 squared minus, right here, I divide it by 2, and then I divide that by 500. And I get a negative 0.5 meters per second squared, right? So he's decelerating, right? So we can even say the acceleration of b is going to be negative negative 0.5 I, right? And for a test-taking strategy, you should try to just write that out right there. There's a bunch of different points right there just for getting to that part. Right? There's a constant acceleration problem. All right, now we want to find out where A is going to be, right? In order to do this, he's traveling at a constant speed. Oh yeah, oh by the way, RA, we needed RA, forgot about that. The radius of this was, I just had 350, so I used 350 meters. So we need to find the time in order, because he's a constant speed, we need to find where he's located around this circle when this guy is right here, when B is right there. So we need to find the time that's between there. So now that we have the acceleration and the initial velocity and then final velocity, we could say VB2 is going to be equal to VB1 plus the acceleration of B times time. Right? So we could just go ahead and stick that in there and say 20 equals 30 plus negative 0.5 times time, and we can solve for when that's going to happen. So that should be able to negative 10 divided by negative 0.5, right? So 10 divided by 0.5, you should be able to do that in your head, right? But didn't, right? So that's going to be 20 seconds, is that right? Put my time, yeah, 20 seconds. 20 seconds. So now we got to find out where the plane is located along there. So let's see how, let's call this delta, this arc length right here is going to be delta SA. So you know, we're using the constant velocity expression, which would usually look like this right here, right? Velocity times time. But let's just put this over to the side and say delta SA is just going to be VA times time, which is going to be, what did I say? I used 40 times 20. So 40 times that is 800. Right? So it has traveled 800 meters. but whereabouts is that as an arc along the curvature of that thing? So we're going to say the amount of angular motion that he has made is delta SA over RA, or 800 divided by 350. These are going to be radians. So we get 2.286 radians. I have to decide. So it's not, remember 1 radian is 180 degrees. So we can figure out how many degrees this is going to be by taking it and multiplying it by 180 and dividing it by pi. So 180 times that and pi divided, you get that this is 130.96 degrees. And so it has not moved past this point. It's somewhere over in here, but so it's down in this quadrant right here somewhere. So it's like traveling like right there, right? So we could subtract 90 from this. If we subtract 90, we could find what the angle is going to be, right? And so that angle is really going to be like this right here is what we're going to find. So we get that 130.96 minus 90. We get 40.96 degrees. That's its location, moving around right down here. Now we want to get the acceleration. All right, now that we have this position, let's get the acceleration. So we know it's going at a constant speed, so its velocity of let's call it acceleration of A is all going to be in the normal direction, right? So it's the VA squared over rho, which is going to be the same thing as RA here. So we're going to have 40 squared divided by 350. And once again, I want to address test-taking strategy. If you just write that down, you're going to get some points, right? So, and you should recognize he's traveling in a circle, so that's a path coordinates problem, right? You want to try to maximize the amount of points that you get, even when you don't know exactly the path that you have to go to solve the thing. Just get some stuff that you know written down. All right, so here's the acceleration that it's going, and it's going towards the center. So this is actually coming that way at that 40.96 degrees. That's the reason why I actually found it. So now we can say that the acceleration of A is going to be this, let me see if I got the right numbers too. Yeah, I think I did. And the x direction is going to be 4.571 times the cosine of 40.96. And we could have done like a coordinate transformation for this, but this is simple enough that I didn't expect people to do it. That would have sucked up some time. 40.96 and go J. And again, this is meters per second squared. So we get the acceleration of A in 40.96 cosine times, and I get 3.452 I, and that's going to be plus, swap them around, 4.571, 40 point, I already had it in the company, I'll put it in there, right. And I think I get 2.996 J and squared. And lastly, we wanted to get, the whole point of this was to get B with acceleration of B with respect to A, which is just B minus A, right? So remember that B, we got all the way up here, was a negative 0.5. And we're subtracting out a 3.452. So that's I. And then there's nothing to do there in B, right? So it's going to be 0 minus 2.996. j. So the answer to this one is going to be, see, do I still have it? Was it flopping? Yeah, okay. So I can take 0.5 and I can just add it to that. So we get negative 3.952 I plus negative 2.996 j meters per second squared. So that was the answer to problem 2. And so it was another 12 minutes maybe, because it's 25, maybe it's a little less than 12 because it was a little more than 13 going in there. Alright, and so like the last problem here is 5 more minutes till 2. 5 more minutes into my office hours, so I better turn that on soon. Alright, so we have this pulley system right here, and this motor is dependent on time, right? So the time it moves, and it has some type of controller that says that it's a function of time. And we want to determine when the block C has moved up some known delta YC, right? So what we have to do first is do one of those also fun diagrams, dependent motion problems, right? So it looks like something like this right here. And you could have written on your exam right there if you wanted to make it speedier here. So it stops right there, right? And then we have another line that comes up to this, right? So you didn't have to take the time to do this, the part of it right here. And then I said, well, it's going to go over to this pulley right here and connect to, here's a drum on a motor, right? And here is the point A right there. And let's see, here's C right there. So here's what I suggest that you do for this is you make a datum right here. The distance between here and here never moves, so we could just treat that as a constant. We can call this YC, and we'll call this distance YB. We're over to the side, and I'll call this XA. So we get there's 2 ropes here. There's this guy, and then there's this guy. So on the first rope, we say, okay, YC right there. But this one right here, there's 2 of them, and both of them are going to be YC minus YB. So that ends up being 3YC minus 2YB, right? L1. And then we could take the derivative of them and get 3VC minus 2VB. Take the derivative again and get 3AC minus 2AB. And of course, we might want to notice that we have VC is going to be equal to 2/3 VB. Same thing with the acceleration. VC is going to be 2/3 AB. Okay, and we want to use those equations later here. So, oh, I don't want that one. I want to peek at that one. Okay. All right, and so let's do the other cable. That's a simple one. Like I said, this is a constant right here, so we're going to just lump that in. So we have YB plus XA. That's all there is to it. And so take the derivative, VB plus VA, and take the derivative again, acceleration of B plus the acceleration of A. So we know that B is equal to negative VA, and AB is equal to negative AA, acceleration of A. And we can combine these together and say the VC, so we don't really care about the position of YB of b right here. So let's get rid of it by putting those in, right? So we have a negative 2/3 VB, and then we have acceleration of c is equal to a negative 2/3 acceleration of a. I didn't mean to be. Like I said, we don't care about b. So we got rid of them. All right, great. So now we got to try to figure out what the motion is of a. Now there's like the little tricky kind of thing. It's like c is the thing that moved, right? But we know that VA is a function of time, which is going to be k times t squared, right? And the k that I used for mine, and let me pause this a second and get my office hours moving along. Just 1 second. Okay, back onto this. Let's see. So we know this here. So one of the first things we want to do is try to figure out when this thing has moved up, because this thing is a function of time. Well, what we could do now is we could replace this with, we know the relationship to VC, right? So I wrote this out much easier to read. So we know that the velocity of c is, with respect to time, would be, and I'm going to ignore the negatives right here, right? So they're not necessary for us. It's going to be 2/3 VA with respect to time, right? So let's just say that it's going to be equal to 2/3 KT squared. And I said, I did say, what did I use for K? I used K is equal to 3 for me. And I think the units are meters per second cubed, right? That would get you meters per second, yeah. And that I said the delta YC I was going to use, I think it was 7 meters, right? So how do we get the time from this? Well, we use that velocity is equal to I'll call it dy dt, right? Because we're dealing with the vertical thing right there. So we could say that dy is equal to v times dt. We can integrate both of those things, and that's going to get me that delta y that I'm looking for. And we'll say right there, and it's going to go from 0 to yc, but that's just going to be delta y, the whole thing. And this right here we can replace, and we can go from 0 to some time, and put this function back in there. So we go 2/3 times k, which is 3 for me, times t squared dt. So I integrate both of these, and I get delta yc is going to be, well, that 3 cancels out, that 3 cancels out, but we're going to have 2. This is going to raise up to the 3, so it's going to be 2/3 t cubed, right? I think I did that correctly. So knowing, we could flip this thing around and say it's the cube root, right, of delta y. So I'll go 3/2, right? It goes back over there, and delta y is 7. So for that, I go 7 times 3 divided by 2. Now I need to do that, and I bring them back up to there. And I say that this is going to be 2.190 seconds. Let me double check my numbers to see if I made some mental error here, which is quite often is the case. Let's see. I don't know. I'm starting to question myself here. Oh, I got it. Okay. Yeah. Yes, it's. I got the correct thing. I didn't fix these over here. Boom. Yeah. 2.190. Great. And okay, so I know this time. Now I can figure out the acceleration of this using the same information that I had up here. Right, so now I want to have acceleration. Let's say I want to find the acceleration of A. We know that the acceleration is dv dt, right? So I can find the acceleration of A just by taking the derivative of kt squared right there, right? So we get 2kt is the acceleration right there. And we know that the acceleration of C is going to be 2/3 the acceleration of A. So it's going to be 2/3 3 times the time I figured out, 2.190 squared. Did I do all that right? I think so. So if I square that and just multiply by 2, because my 3's canceling out of 2, and I should say that 9.59 meters per second squared is going to be my acceleration. And I think that's all I was asking for in this problem. Let me double check what this thing said was going to be. Boom. Yeah, determine the acceleration of block C after it's moved up there. So there you go. That's the solution to this, and it was a 36 minutes. I try to go for a factor of about 2 for second semester sophomores. So it's about what I expected for a time frame. So there you go.